Okay, so in this video, we're going to introduce this concept of the big O. Uh, what is big O and why do we need it? So it really has to do with algorithms. Now, we won't actually be analyzing the algorithm itself. We're really going to be focused on the growth rates of the algorithms. All right, so here in general, this chart you see here, it kind of maps out it's called the complexity chart of Big O, and what we're interested in is these growth rates and classify the growth rates. All right, so if you look here, there are, and again we'll get more into this notation here, but we could see if we classify an algorithm in a certain type of growth rate, that's more efficient or faster or slower than others, depending on the type of algorithm. Right? I think here, when an algorithm is introduced, right, people are generally good at learning how to make things efficient, but what is kind of difficult to do is find, well, how efficient what is the lower bound of the efficiency here? Right? So what we have is just kind of comparing these growth rates of different types of algorithms, right? Now, a good way to visualize here. Now, one thing that we, oh my God, excuse me. All right, now, one thing that we are going to focus on is we only care about in the long run, right? So when we're out here, right? We are not going to care so much for small values, and again, large values in like thousands, in the thousands, right? So as we see here, once we start, certain cases, some of these, especially out here in the ON and the O log n, big O log n, right? They might look like one of them, especially the O log n looks like it's faster to begin with, but again, if you see in the long run, it's actually the slowest of all these growth rates here, right? And then here, a good way to visualize this here, if we do, actually, let me go back here. Okay, all right. Okay, so if we look at this here, so let's look. Okay, all right, okay, got it, okay. All right. So if we look here, this is just a visualization of the bubble sort, which is a rather slow algorithm. Here, if we here random, all right, and if you choose kind of sort, all right, and this one has I think this is a big O log, if I remember correctly here. All right. Now, as you see here, you can see a visualization of a bubble sort of what's going on here. And kind of we're looking at growth rates. Another algorithm we could look at is the merge sort. So here, random. As we could see here, this one has a much faster growth rate. Again, the amount of elements is rather low, so there's not a huge advantage at this size here, but we can see the advantage as it grows, right? As we increase the number of n, then we could see this kind of take place, the separation of the growth rates here. But as you can see here, it's even starting to work here rather quickly, right? Whereas this here is going through one of the passes here in the bubble sort, and it's going to redo this and reshuffle till it eventually gets sorted here. Right? Whereas this, as you can see here, right, the merge sort, you can see we're getting a lot more progress here. All right. So the idea of big O, we're not going to be in depth into the algorithms themselves, but just really how to calculate the growth rates of them. Right. And a couple things here that we are going to focus on is that we only care about the long run. Right. So only the long run matters. Right, so here, only the long run matters. All right, so if we have, let's say, our functions, f of x, f naught of x equals to x squared plus 5x plus 6, and f1 of x equals to x squared, right? Now we could plot both of these, right? And we could see, well, one of them may look kind of bigger to begin with, but if we think of as x grows bigger and bigger, right, as x goes to infinity, if we look at the ratio of f0 over f1, right, then this is going to be 1, right? So here what happens is that these terms, as x gets larger and larger, they become insignificant here, all right? Now, another criteria is that constant factors are ignored here, right? So here, especially like something like this, like let's say if we redefine, so f naught will keep the same. And let's say f1, or we'll call it f3 now, just to here. We'll call that 2x squared plus 3x plus 4. Okay, so again, right, in the long run, like these values won't play much into the growth rate. But if we take a look at f3 over f0, right, now this doesn't equal 1, this is equal to 2, right, as x goes to infinity. Right, again, if we recall our limit studies from calculus here, now this goes to 2. Now in the big O context, these are treated to have equivalent growth rates, and mainly what we're focused on is the fact that they are bounded. Right? Not so much the number, but the fact that these are bounded numbers. It's not infinity or something like that. Okay? Where in contrast, like let's say we had f of 2 of x cubed plus 2x plus 3, right? If we do f of 2 over f naught, right, now this one, as x goes to infinity, right, we see analyzing here what we have is essentially is a rational function with a higher degree in the numerator, so that is going to tend towards infinity. Okay. All right, so these do not have equivalent growth rates, right? Now here, this is what is classified as unbounded. Okay. So when we're dealing with a big O, one thing to remember is that big O ignores behavior for small n. All right, and here, before we move on, we can check into our sorting. I'm going to see here the bubble still going, doesn't even look like it's close to being done here, right? And as we see here for the merge sort, all right, you can start seeing here at least this part here, right? Much more sorted, right? And as we'll see, and then sticking around here, let's maybe speed this up here. Actually, here, not that part. All right, you could see there. All right, you can see it moving faster, right? I sped up the speed, but you can see even at this rate, you can see how much better the merge sort is at doing this than, as we can see, even the bubble sort, even though it is moving at a faster pace, right? Its growth rate, it's not close to getting there. All right, so back to our big O, it ignores small n and constant multiplicative factors. All right, so the complexity function is a real valued function that is defined for all sufficiently large n, inputs and is eventually non-negative, right? So big O, when we talk about big O, we say f, our function, is big O g, big O of g, when there exist constants n, c, element of the real numbers, such that for all x greater than or equal to n, right? So at some point, right, this behavior sticks, right? Maybe at the beginning it might not be clear, right? But at the end of some point, right, then that is true, right? So what happens that for both f of x and g of x, the absolute value of f of x is less than or equal to the absolute value of g of x, with the exception of some constant factor of c being multiplied by it. Right? So we can think of O as the less than or equal to for growth rates, right? F is big O of g, means F's growth rate is at most g's, right? So this is the bound that we've been talking about, right? The function bound. Okay, so while it might not be exactly the same, but it can be at as most the size of whatever g is, right? So for example here, here, we say, all right, so if we let f of x be equal to x squared, and g of x to be equal to x cubed, all right, f is big O of g, with n equal to 2 and c equals to 1. Okay. All right. So after 2, when x is 2 here, then that value of x cubed will be larger, right? And it doesn't start out that way, right? So, but again, remember, in the short term, it does not matter. We just care about in the long run, right? So for x greater than 2, right, we could see here that if g of x is equal to x cubed, which is equal to x times x squared, right? So that's going to be greater than here 2x squared, which is greater than x squared, which is our f of x. Okay, so we could see that our function f of x squared is in this case less than g of x, right, with some constant, in this case 2. Okay, all right. So here, another way to think, another example that we can look at here is, let's say f of x equals to 5x squared, right, and g of x is equal to x to the 4th, right? And we'll take here in this case also n is 2, and we'll take our c to also be 2. All right, so when we verify when x is bigger than 2, right, this gives 2x to the 4th is 2x squared times x squared, which you say here is greater than or equal to 8x squared, which is greater than 5x squared. All right. Okay. All right, and we can see that that inequality holds, right? Now be careful here, right? A smaller value does not mean a smaller growth rate, right? So g of x equals to x squared is less than x squared plus 1. All right, that is true, right? We're taking squared and then we add 1, right? So g of x would be less than that function, but again, that doesn't matter in terms of big O, okay? Even though this is true, these have equivalent rates. All right. Okay, so here, just kind of finishing up here, checking in. Here we could see our bubble sort still working, right? Getting better. But here we could see the merge sort, right? Almost completed here. All right, so there's also something called the big theta as well, which we don't get much into here, but just to keep in mind that there are other of these functions that deal with growth rates. All right, so when we talk about what the idea behind big theta, right? So we say f is big theta g when f is okay. All right. F is OG. Oh, great. Okay. Yeah, that's sorry, having technical issues here. Okay. Well, okay, kind of. All right, so my apologies. There's something wrong with I'm not exactly sure what's going on here, but I did just want to wrap this up. There is a big theta G, big theta of G, right? When we have equivalent growth rates, it is actually also an equivalent relation, what is reflexive, symmetric, and transitive, right? But we won't delve too much, or really much at all, into big theta. What we are going to focus on is the big O, right? Where we compare long-run growth rates. And again, as always, when dealing with these, we ignore constants and small inputs, right? Next, we will show how to actually compute big O. And the tools we're gonna use for that is limits and L'Hopital's rule, right? And we'll establish the hierarchy of these complexity classes, right? Which one grows faster than which other ones? So similar as we see here, right? In our complexity chart. So we'll establish these, we'll write this down to calculate our growth rates.